I presented the first and third laws in the previous lecture. Let us now have a look at Newton's second law. It is easiest to express this law with an equation. F net equals ma. It means that the acceleration is in the same direction as the net force because m is a positive scalar. The measurement unit of force is the product of the measurement unit of mass and the measurement unit of acceleration. So it is kilogram meter per second square. And this combination of measurement units is called a Newton. In the imperial system, mass is measured in slug and length in feet. So the measurement unit for force is the pound, abbreviated as lb. Newton's second law equation links kinematic to dynamics. It links a feature of motion, the acceleration, to a quantity explaining motion, the force. We can now quantify forces with this equation. At the surface of the Earth, an object that is free-falling has an acceleration equal to g, which was 9.8 meters per second square, downward. For a projectile, the net force equals the weight of the object, as it is the only force acting on the object. We quite regularly neglect air friction in this first approach to projectile motion. It would complicate things too much. So, using Newton's second law, we write that the gravitational force is equal to mg. Let us do an example where we want to evaluate the gravitational force exerted on a 2 kilogram object. Here is our list of givens. And using the equation Fg equals mg, with the givens, we get that the gravitational force is 19.6 Newton downwards. Now that we know how to evaluate the gravitational force of objects near the surface of the Earth, we can use that to calibrate a spring. The device that measures the force that a spring exerts is called a Newton meter. It consists of a spring that has a way to attach itself to a fixed location like the ceiling and can hook an object underneath it. It is enclosed in a case that lets you see the spring. A marking of 0 Newton would be present at the position where the spring ends when it is relaxed. If an object with a weight of magnitude of 1 Newton is attached underneath the Newton meter, the end of the spring should come to rest beside the marking for 1 Newton. You can also have more markings corresponding to different values of forces. This procedure is called calibration. Once this is done, you have a device that measures forces. A word of caution about the use of the Newton meter. First, they rely on the stiffness of the spring to be constant. Second, if the purpose is to measure the weight of an object, then the object hanging off the Newton meter should not be accelerated. Otherwise, the net force is not 0, and the reading on the Newton meter is not equal to the gravitational force. So beware of measuring your weight on a bathroom scale inside an elevator. Finally, some Newton meters are calibrated with markings labeled with measurement unit of mass, such as gram or kilogram. An assumption had been made here to the effect that the Newton meter should be used at the surface of the Earth, where the magnitude of the freefall acceleration is 9.8 meters per second square. For example, bringing a Newton meter calibrated on Earth would give the wrong value for the mass when used on the Moon. In summary, remember that what the Newton meter measures is the magnitude of the force that the spring exerts. In the previous lecture, we had reached this relationship of proportionality, which cannot be used to get a numerical value for the gravitational force. We can turn it into an equation by adding a constant of proportionality. Let us use the letter capital G for this constant of proportionality and write this equation. In order to evaluate capital G, we need an experimental setup where Fg, Ma, Mb, and R can all be measured. This is what Lord Cavendish did 110 years after Newton presented his theory of gravitation. Basically, he started with a torsion balance, which consists of an horizontal rod suspended above the ground by a metal wire. 2.73 kilogram lead balls were suspended at each end of the rod. The twisting of the metal wire would offer resistance to the rotation of the apparatus, and Cavendish established the relationship between the horizontal perpendicular force exerted on the balls necessary to rotate the apparatus by a given angle theta. I do not intend to explain how this calibration of the torsion balance was done. It would involve material that we have not yet covered. There was another pair of lead balls suspended by metal rods on either side of the torsion balance. They were much bigger balls since they were about 150 kilograms each. This is a side view of the apparatus. Let us now look at it from above. Here is the rod supporting the small balls. Here are the bigger balls and their supporting bar. When the bigger balls were positioned near the small balls, the rod would swing to bring the small balls closer to the big ones. The angle of that swing was measured through the telescope from the right. So Cavendish knew how far the small balls were from the big ones, and he knew the mass of all the balls. And through the measured angle, he could get the force of gravity exerted between the small ball and the nearest big ball. His data led to a constant of proportionality G near 6.673 times 10 to the minus 11 Newton meter square per kilogram square. Or if you use the fact that 1 Newton is 1 kilogram meter per second square, you can write it this way. This constant is now known as the universal gravitational constant, and I have given the value established by more precise methods. By the way, there are still experiments being performed to evaluate the value of G more precisely. And the nagging thing is that G does not seem to be that constant, but I will not elaborate on that. Actually, Cavendish did not evaluate the universal gravitational constant, even though he could have with the data he had collected. The concept of the gravitational constant only became popular 90 years after he performed his experiment. His purpose was to evaluate the average density of the Earth. Let us see how it could have been done. We will define RE as the distance center to center between the Earth and a small object near the surface of the Earth, ME as the mass of the Earth, M as the mass of the small object, G as the magnitude of the freefall acceleration at the location of the small object, dE as the mean density of the Earth, and finally VE as the volume of the Earth. We have two ways of expressing the gravitational force: the expression we have just derived and the gravitational force derived from Newton's second law. The two expressions should be equal to each other if the small object is free falling. Isolating for ME gives us a way to evaluate the mass of the Earth. Using the current values for RE, G, and capital G, we get the mass of the Earth to be 5.96 times 10 to the 24 kilogram. Here G and capital G are considered to be constants and not influencing the number of significant digits of the answer. Note that we didn't have to put the Earth on a scale to evaluate its mass. And onto the evaluation of the average density of the Earth, which is the ratio of the mass and the volume of the Earth. Assuming that the Earth is a sphere, we can use the formula for the volume of a sphere in terms of its radius. Simplifying this expression gives this, and substituting the givens leads to a final answer of 5,500 kilogram per meter cube, which is 5.5 times bigger than the density of water. Cavendish found from his experiment that the density of the Earth was 5.48 times bigger than the density of water. Let us practice using our new expression for the gravitational force in a numerical problem. Essentially, we want to know how far from the Earth do you need to go to be attracted to the Moon just as much as you are attracted to the Earth. Let us first define our variable names with a drawing. Here is the Earth with a mass me. Here is the Moon with a mass mm. Here is you with a mass m. The distance between the Earth and the Moon will be labeled RO for the radius of orbit. The distance between the Earth and you as RE, and the distance between you and the Moon as RM. A gravitational force FGE is exerted on you by the Earth, and a gravitational force FGM is exerted on you by the Moon. Our givens can be found in astronomical data tables on the internet. Here are some of the values that might be useful: the mass of the Earth, the mass of the Moon, and the radius of orbit of the Moon around the Earth. The mass of the Earth is only slightly different from the value that was calculated on the previous slide. In order for you to be weightless, the magnitude of the gravitational force exerted by the Earth must be equal to the magnitude of the gravitational force exerted by the Moon. Now, using our new way of expressing the gravitational force, we can write this. Noticing that capital G and M are on both sides of the equation, we can remove them from the equation, and we can also remove Rm by noticing from the drawing that it is equal to Ro minus Re. The next step consists in rearranging the equation so that all the factors involving distances are on the left-hand side and the quantities involving masses on the right-hand side. Next, we take the square root on both sides, only keeping the positive root as the only one making physical sense. Now, collecting the Re together leads to this, and isolating for Re gives us this expression. We can now evaluate Re in terms of our givens. Before we do so, notice that if the mass of the Earth was equal to the mass of the Moon, then the denominator would equal to 2, and Re would be half of Ro. It would mean that the place where you are weightless would be right in the middle between the Earth and the Moon. But the mass of the Moon is smaller than the mass of the Earth, which means that Re is greater than half of Ro. The location where the gravitational forces cancel each other out is closer to the Moon than to the Earth. Here is the expression for Re that we had arrived at on the previous slide. We can now substitute the givens and find a numerical value for Re. This is our final answer. Notice that Re is 90.1% of the value of Ro, so much bigger than 50% of Ro. Before we move on to study numerical examples of problems where the situation demands a net force that involves more than the gravitational force, we need to define an important concept called the gravitational field. This will be the subject of the next installment.